All right, well, we've reviewed chapters 1 through 9 in the last lesson. I asked Quentin before we started the video, was there anything we needed to go over again? And he said, no, I think I've got it. So if that's not you, if you, in the last lesson, as we were reviewing, were like, I need more help on this, reach out to me, get the help, because when the exam comes, it's too late. Get the help now. Okay, there's no help after the exam. But Quentin's good, so we're going to press forward into chapter 10. We talked about analytic geometry. And remember, we said there are three major analytic tools: intercepts, symmetry, domain, and range. Now, intercepts, the key was to plug in...
Why? No. Plug in zeros.
Plug in zeros to see where it's going to cross the axes. Because where there are axes, there are zeros. Everything along the x-axis has a y value of 0. Everything along the y-axis has an x value of 0. So you plug in zeros, you're going to find your intercepts. For symmetry, what do we have to plug in? Well, kind of. Plug in a negative, remember. So to determine if it's symmetric to the y-axis, plug in a negative x and see if it's the same as a positive x. For x-axis symmetry, we said plug in a negative y. And if a negative y is the same as a positive y, it's symmetric to the x-axis. And then for origin symmetry, we said plug in negatives for both. Because if both the negative are the same as both positive are good, or if one negative is the same as the other negative, then we've got that origin symmetry. And then for domain and range, again, domain is defined as all possible x values, but to determine which x values are permitted, we said the best thing to do is set the equation equal to y. And that gets the y out of the way, you can focus on the x. And for the range, which is all possible y values, or f of x values, if we're in functions, these weren't yet, we said set the equation equal to x, and we can focus on the y. So for instance, if we had x squared minus 9 is equal to y, and we wanted to find the x and y intercepts, we wanted to determine symmetry to either the x-axis, the y-axis, or the origin. And we wanted to find the domain and the range. This chair there, talk me through this, Quentin.
So for the x-intercept, we plug in 0 for y. So x will be positive negative 3.
Good, move that 9 over as a positive, take the square root, you get positive negative 3. Or factor when you plug into 0. X plus 3x minus 3 gets you positive negative 3. What about the y-intercepts?
Y-intercept, plug in 0 for x, and y equals negative 9.
All right, x-axis symmetry, we said.
Put in a negative y.
And if we put a negative right here,
it changes, so no.
No, it doesn't stay the same with the negative in the y spot. Okay, what about in for the y-axis?
Negative x, yes.
Yeah, it stays the exact same because that square just changes it back. And then for origin symmetry,
since x was no, origin is no.
Yeah, if both of these are no, you could have a yes here. But if they're different, if one's yes, one's no, you're definitely getting a no here. Again, you could plug in the negative. It works, but this one doesn't. So again, it's not going to happen. For the domain, we said we want to set the equation
equal to 0. Well, set x equals no.
Set the equation equal to y. Set it equal to the other letter. See, remember, for intercepts, you plug in 0 for the other letter. For symmetry, you plug in negative for the other letter. And for domain and range, you solve for the other letter. Since domain is x values, we solve for y, which is already done. And we ask ourselves, well, what can I put where the x is? Anything, all real numbers, negative infinity to infinity. Though it's faster, I think, to say all real numbers. For the range, since it's all of your y values, you want to
set it equal to
the other letters. So set it equal to x. So to set it equal to x,
so move the 9 over x squared.
and then ask yourself, what can I plug in for the y? Good, it's not all real numbers. A negative 10 is a problem. In fact, a negative 9.000001 is even a problem, because it would still give you a negative. You can't have square roots of negatives. So as long as we have at least a negative 9 or greater, we're good to go. Do the same analysis now on 3x squared negative y squared equals 12. Take a few moments to work this on your own, and then we'll go over it together. Intercept, symmetry, domain, and range. questions on the first sections? All good to go there? All right, and then for the domain, I hadn't gotten there yet, so we'll work it now. I'm going to do a double switch. I'm going to do 3x squared minus the 12 equals y squared, and then take the square root. Basically, this x squared needs to be at least a 4, which means I need at least a 2 or negative 2. 3 or negative 3, 4 or negative 4, but I can't use a 0 and I can't use a 1 or a negative 1, right? So my range is going to be negative infinity to negative 2 or 2 to infinity. And then for the, domain, the range is going to be, let's see, I'm going to kick out the y squared as a positive, divide by 3, take the square root. Well, here, no matter what I plug in for y, it's going to be positive because I'm squaring it. Added to 12, it's going to be more positive. Divided by 3, it's still positive. So that's going to be all real numbers on that one there. All right, good to go on that. Question, Quentin. What shape do I get right here?
A hyperbola? No.
X squared minus 9 equals y.
That's a
parabola. How should we be able to tell, even without doing the analysis, I'm getting a parabola?
The x squared, y isn't.
Right, 1 over squared, 1 isn't. Now, if it said x plus 3y squared equals 8, would that be a parabola?
No, because it's being added. Wait.
It still would. It would just go sideways. But if anytime 1 is squared and 1 isn't, added, subtracted, doesn't matter. If they're 1 squared, 1 isn't, it's always going to be a parabola. Now, here, they're both squared, and they're subtracted. We don't even get any y-intercepts. What do we end up with here? If they're squared and subtracted.
That's the ellipse. No.
That's our hyperbola, right? They're squared and subtracted. That's the hyperbola. So coming over here, what if they're squared and added together?
Ellipse.
That's the ellipse, or this. Let's see. In this case, it would be this kind. It'd be a horizontal one. What about this one? They're squared and added again. Is that also an ellipse?
Circle.
Why a circle and not an ellipse?
Because they have the same numerical.
They have the same numbers, so this would actually just be a perfect circle. What about right here? Neither one is squared.
Straight line.
That's a straight line. That's linear, isn't it? Now, specifically, this linear equation is in the ax plus by equals c, or what we call the... This is chapter 11 now, by the way. The general form. The general form. Looking here, notice in this equation, it's also x to the first and y to the first. So this is also linear, but when they're written in fractional form, set equal to 1, we call this the intercept form. The intercept form. This last one's one you should recognize from years past. This one should be a little bit easier for you. Again, they're both to the first power. So again, it's a linear equation. In this case, we would call this the slope-intercept form. So again, if it's just x, y equals number like we used to do in our systems of equations, that's the general form. That's the best looking form. This kind is intercept form. Your guaranteed fractions is going to be equal to 1. That's slope-intercept form, y equals mx plus b. If you introduce squares, we get into quadratic equations. Your basic quadratic is only 1 square. That's your parabola. That's what we studied in Algebra 2. But if they're both squared, it could be a circle with matching numbers. Could be an ellipse with different numbers, but still positives. And the weird one is, you work a negative into one of these, we go hyperbola. And we spent chapter 12 specifically studying the non-straight line. So chapter 11 was all of this, the straight line forms. Chapter 12 was all of these, but we went into a little bit more depth with those. And that's what we're going to focus on next. Questions before we hit chapter 12? All right, so let's get to chapter 12 then. And if you have graph paper, go ahead and get it out. Now, I'm going to have to do freehand sketches. We're moving classrooms pretty rapidly today with our exam review, so I did not have an opportunity to, well, I didn't think to be honest. I'm a failure. But we'll say I didn't have a chance to grab the graph grid. So get your graph paper out, and I will have to freehand sketch my graph here, and we'll try to make it not look terrible. But you're going to benefit from graph paper. Obviously, on the exam, you'd have the opportunity to graph. And we do need to remember how to analyze and graph, for instance, a parabola. We had something like this: y squared, negative 4x, positive 6y, positive 13 equals 0. This is, of course, a parabola because
the y squared and x isn't.
Only the one variable has a square. And with this, what we said we want to do is get all the squared together, that variable that is squared together, and everything else on the other side. So?
Y squared plus 6y equals 4x minus 13.
Good, and you can work this along with me there at your seat. Kind of talk me through as you work. What will we do next?
Complete the square.
Complete the square. All of our conics, we ended up completing squares. So?
Plus 9 on both sides.
Which really means that right here we get a
Negative 4.
All right, now what?
Backwards 4. Or
binomial squared. We could technically just be the same thing twice. It's better to be binomial squared.
y plus 3 equals 4 times x minus 1.
There we go. So we do a factoring step. And once we get this, this is in the form that we want to see. Because from here, I can see where the vertex of my parabola is going to be. Be very careful.
It is going to be at 3? No. 4.
All right, so remember, this here is my negative y1. This here is my negative x1. And the vertex is x1, y1. So
1, negative 3.
1, negative 3. Remember that now? All right. And then we need to ask ourselves, well, which is the axis of symmetry for our parabola? And it's whichever one is not squared. So in this case, the x-axis is the axis of symmetry. Then we had a, remember in a parabola, we have that special point, we talked about in physics, that really helps to define the parabola. It's called the focal point, the focus. And from the focus, we have a line called that principal, that primary axis, that axis of symmetry that runs through the focus and through the vertex. And however far the vertex is along that line from the focus, we call that the focal length. We represent it with the letter P, remember. But this value isn't P. This value is 4P. So what is the focal length of our parabola?
1.
1. A positive 1, which on the x-axis means forward 1. Then through the focal point, we had a focal chord called the Latus Rectum. What we wanted to do was find the length of each half of the Latus Rectum. Now this 4P equals the Latus Rectum, so we would cut it in half. And so we'd say each side is 2. Or we could double the focal length. Either one would give us that. So for our graph then, we would start by plotting the vertex at 1, negative 3. So that's going to be forward 1, down 3. And my suggestion was, as you graph, go ahead and draw your translated axis of symmetry. So we're going to lightly draw here a little x prime axis. And then along that x prime axis, starting at the vertex, we're going to go
Up 1.
not up 1, it's on the x-axis. So forward 1 to the focus. And by the way, if from the vertex you go forward 1 to the focus, you have to go backward 1 to the line that helps to define the parabola called the directrix. And then parallel to the directrix, perpendicular to this axis of symmetry, we have the latus rectum, which is 2 each direction. So we're going to go up 2 and down 2 to the end points of the latus rectum. And remember, we're going to go through the latus rectum and there's our parabola. Okay, take just a moment to sketch that. You can pause the video if you want to. We're going to give Quentin just a moment to work it though, so you'll be able to keep going. It's been a while. I mean, visible rust here. Questions on this?
No, I remember now.
Yeah, this may be something you may want to go back and watch some old videos. I mean, it's pretty easy if you go through the playlist to find, just kind of scroll through till you find in the description something about parabolas. And you might be able to go back and kind of just refresh your memory on that. Or if you find the review for Test 11, the Test 11 review lesson, we'll go over all the conics at once. That might be a really good lesson to go back and rewatch. But we'll do some more review even in this lesson. The next thing we talked about, rather, after the parabola, of course, we talked about the circle, but that was really easy. It's just center and radius, so I think we've got that pretty well. The ellipse was the next one we talked about, and I can tell just by writing this much that it's an ellipse, because
both are squared and they have different numerical values.
They're squared, they have different numerical values, and they are both positive, right? They're both added together. So squared, added, different numbers. So here we have our ellipse. All right, again, like the parabola, we want to kind of get our letters together here.
9x squared minus x, or 18x, leave the space. Then 4y squared plus 16y, leave the space, equals 11.
Good, but before we can complete the square, we have to factor out common factors from each set, remember.
So, 9, and x squared minus 18.
Ooh, careful, we're pulling the 9 out.
Oh, minus 2x plus 4.
Half inch square?
1.
All right, it's okay, we're shaking some rust off here.
And then pull out 4. Y squared plus 4y, y squared plus 4y plus 4. Then you're going to add a 16 and a 9 on it.
Good, it's not a 1, it's a 9. It's not a 4, it's a 16. So you're going to have the 9 and the 16 so that right here we end up with a 36. Again, you're working along with me here. But then one of the key characteristics of both the ellipse and the hyperbola is in order to get the proper form, I need to set the equations equal to
0 or 1.
1. Right, so to set the equation equal to 1, I've got to divide all three parts by 36. Now it's going to give me a 1 on this side. Here, the 9 and 36 cancel to give me a denominator of 4. But instead of writing the PST, I'm going to write it as a binomial squared.
X minus 1 squared.
And then right here,
Y plus 2 squared
over 9. You said 9? And there's my elliptical form. All right, so at this point then, we're ready to go and analyze this thing. We want to know, where is the center of the ellipse? X1, Y1.
Negative 1, 2.
Careful.
1, negative 2.
Right, remember the form calls for a negative, so if we see a negative, it's positive. If we see a positive, it's negative. I kind of can think opposites there. Which axis is the major axis going to be along?
Y-axis.
The one with the bigger number, remember, major means it's bigger, so it's the y-axis. How long is each side of the major axis?
3.
3 each side, total of 6, but 3 each side. That's usually what we did in class. How about each side or each half of the minor axis?
2 each.
2 each. And then we come to the focal length. The focal length, remember, in an ellipse measures from the center out to the 2 foci that define the ellipse. How do I find focal length for an ellipse?
Was it square root of the square? Yeah.
Square root of a squared minus b squared, remember, for an ellipse. So here's my a squared, there's my b squared. I end up getting the square root of
56.
Careful. This is a squared.
Oh, okay.
And this is b squared, remember. So
Square root of 5.
square root of 5, which is about 2.2. And then for the half lateral recta, that's a b squared over a. The smaller number divided by the square root of the larger number. 4/3, which is about 1.3. So what we'll do for this graph, remember, is we'll start by putting our center point at 1, -2. We'll draw a new y prime axis here. We'll go along this major axis, up 3, down 3, outward over 2, over 2. We'll go 2.2 to the foci, and then outward 1 1/3. And we'll end up with, it's really poorly drawn, but something like that for our ellipse. Again, if you need to go back and re-watch that review lesson for test 11, do so, but hopefully this shakes a little of the rust off before you do that tonight. Real quick, I've got just a few minutes left over. Let's take a look at the hyperbola. Very similar approach to the ellipse, but there are some nuanced differences I want to make sure we remember even before we go back and do a little outside review. If we had a 4x squared minus y squared minus 8x plus 6y minus 21 equals 0. We know this is a hyperbola because
both are squared, they're subtracted, and
good.
They have different.
Well, you don't even have to have different necessarily, but you do have to be squared and subtracted, right? So we're going to do the same kind of thing we did to start off the ellipse.
So 4x squared minus 8x in this space minus y squared plus 6y equals 21.
There we go. But like the ellipse, we have to factor out some common factors before we can complete the squares.
Factor out 4 and 8 squared minus 2 plus 1.
And what do we factor out here?
-1.
The -1, good. Or just the negative is fine.
Y squared minus 6y plus 9.
But really what we have is a
4 and -9.
a 4 and a -9. So we end up with
16.
a 16 over here. Of course, here we can write binomial squares if we want to, and we do.
X minus 1 squared and y minus 3 squared.
All right, and then like the ellipse, gotta set it equal to 1.
So divide everything by 16.
And when I do, I end up getting a denominator of
Minus 16, but 4.
4. Here I end up getting a denominator of,
16.
yeah, nothing really cancels, just kind of the 1 drops away. And then here, of course, I just get the 1. Now with this, we remember we have what's called the origin of the hyperbola, but it's like the center.
1, 3.
1, 3. And then we have not a major axis, but a transverse axis. And this is based not on the bigger, but on the positive,
So 4.
the x-axis. And then we need to know the length of the transverse axis, or each half, and the length of the half conjugate axis. What is the length of the half transverse axis?
2.
2, the square root of 4. And then the half conjugate axis,
8.
careful,
4.
this is b squared, so b would only be a 4, the square root of that number. The focal length, remember, here goes from the origin out beyond the vertices, which are the ends of the transverse axis. And so the focal length for a hyperbola is the square root of a squared plus b squared. We're going to add them to get the square root of 20, which is about 4.5-ish. And then finally the half lateral recta, the same thing. The half lateral recta, remember, still b squared over a. But remember, this is the b squared. And a is only 2. So we end up getting half lateral recta of 8, which means we're going to have a really flat hyperbola. Just for sake of showing it by way of review, and this is where we'll stop for today. We're going to go to 1, 3. We're going to draw a new x prime axis. We're going to go 2 along the transverse axis. We're going to go up 4 to the conjugate axis, and that, remember, helps me to get the 4 corners of the fundamental rectangle through whence we draweth our asymptotes. Then along the transverse axis, we're going to go a little further, out a total of 4.5. We've already gone out 2 to the vertices. we're going to go out 4.5, so somewhere around there to a focus, and somewhere around there to the other focus. And from there up and down 8, approaching those asymptotes. And remember, we'll approach but not touch, approach but not touch, however that turned out. Up, down 8, something like this, and there we go. Again, I'd encourage you, Quentin, and if you're watching, go back to that review lesson before test 11 to get some more practice with this. Tomorrow, we'll have one last review over derivatives and integrals. Our calculus stuff should be pretty fresh in our minds. So that's why I'm willing to do that. That's the very last thing right before the exam. And then we got our exam. All right, so you know the old stuff that you need to look over. The new stuff, just more of a refresher tomorrow, and then the exam. Any questions, Quentin? All right, well, let your next teacher know I kept you a few minutes over. Have a wonderful rest of your day.